Hi. So to start off with, wish you and your family a very happy and safe Diwali. Welcome to yet another lecture as part of the STEMS 2021 lecture series that is being held in association with the Roots program of the Raising a Mathematician Foundation. Running in the Diwali spirit, we have a very exciting session today by Professor Sayar Karmakar of the University of Florida. The lecture is titled Learning Dependence Independently. This will be a very practical talk about dependence with plenty of applications, as we shall soon see. So before Professor Sayar takes over, here's a quick bio about him. He's an assistant professor at the Department of Statistics in the University of Florida. He obtained his BStat and MStat from ISI and his PhD from the University of Chicago in June 2018. And apart from maths, he's also a huge fan of cricket and traveling. Just a couple of points before we go to the lecture. It would be nice if people could keep their videos on so that we can come closer to having a live session. And if you have any questions, use the raise hand option or type them out in the chat. So without any further ado, sit back and enjoy the talk by Professor Sayar.
Hi. Okay, hi. Yeah, thank you so much. Thank you for the kind introduction and the invitation. It's an honor. It's a pleasure to be able to talk at CMI. Before I begin, this is sort of an informal talk. There won't be a lot of theorems or a lot of data analysis. This is mostly about what we do as like different areas of time series and what we mean by dependence, and then dependence in different applications. And I'll finish up with like some interesting machine learning thing where I think some techniques from time series can help. Uh, I mean, I've kept this intentionally at a level that probably this particular audience can understand or appreciate. And I will be really glad, like, if you stop me or like you can intercept me, you can put a question on the chat. I have the chat button, chat window open here, or you can also ask a question and I'll be able to, you can unmute yourself, you can ask a question. I'll be happy to try and answer that sort of bit. So that's why I do not have too many slides for about an hour long talk. I will really appreciate if you have questions. Just let me know. I'll be able to go back and answer this question. And before I begin, like just a little bit about CMI. So as like a high school student, CMI was really, I think, only one of the two places where I always wanted to be. And I really regard CMI as a place that, I mean, it was always like ISI or CMI for me when I learned about these two places. So I did get an admission at CMI, but never actually been to CMI. That is a little bit unfortunate, but probably this is the first time I'm interacting with CMI students directly in some capacity. So I am indeed really honored for this sort of place. I mean, this sort of opportunity to talk. And I have been like close to CMI students for a while now. So while I was a student at ISI, I've also tutored quite a few students that finally ended up going to CMI. So and they are still in touch with me. Now the CMI has opened this MS in data science. So quite a few students actually who did not go to ISI for their statistics classes, they are actually opting and going to CMI for this MS in data science classes. And I have known faculties from CMI for a while. I've been like very close to the community, but this is probably the first time I'm like actually talking at CMI. I have given talks at like ISI, mostly because of my connections there. I've been a student there but this is the first time I'm talking at CMI. So welcome everyone. So today we'll be talking about time series. Time series is something that I started doing during my PhD. So before I come to that, maybe I can talk a little bit about how the research world works, or like how I got interested in research and what sort of problems I really thought that I would be able to contribute, what were my like progression. The thing is that it is very difficult, like when you are an undergrad student, even like a graduate student at the master's level, it is very difficult to visualize what exactly you could be like an expert on. It's we think something, but something else happens. And usually once you finish your master's, master's program, and then like maybe you are looking for a PhD program. I mean, it's not necessary that you have to do a master's, but for statistics classes, like for statistics courses, at least back in like here in USA, they do require like a 4 years of undergrad. So since we were doing like a 3 years of undergrad at ISI, the norm was to complete 2 more years and then go into the PhD program. And that's what we did. And I mean, it did help us in securing admit to like good universities. Um, so we already had quite a bit of training in statistics like after we completed our BStat and MStat, but at that point of time I did not know myself that I wanted to do like work on time series. So it was mostly like I was trying few problems. I was working on robust statistics the last year of my like at ISI. Before that I was working in some like problems in genetics. I spent a couple months here at JHU, Johns Hopkins University. And so the experiences were like when I worked in JHU, I did not really thought like I would be want like there are really great problems. Genetics is like a really huge data area, but I just thought that maybe I will be I want to do something more theoretical. And at that point of time, then when I went to Chicago after taking my first year classes, then I saw, okay, we have this professor, and maybe I can work with him. And we talked, and then we started working on these problems. And then slowly, and as you know, PhD is indeed a sort of a grueling process of like for quite a bit of time. You spend quite a bit of time, and it takes time to directly jump into something new and learn. But I think it's a gradual process. Also teaches you a lot of other things like resilience and like how you counter a problem, how you solve it, and then how you write papers, blah, blah, blah. So if in case you feel like you want to like talk to me or like discuss something about me, feel free. I always like whenever I give this talk, I sometimes end up getting emails like, are you looking for students in your lab? The thing is like, okay, this is what happens in the statistics department. Not all the departments are the same. Of course, there are some exceptions to this, but typically students are admitted like with the central, like admission process is a central process. So the students are admitted in a pool. Once they are in here, then they look for like whom they can work with in the department. And it's difficult to like, I mean, it's not really in some other subjects you contact the professor, and then the professor, if they are looking for some student, they take it. It's somehow I felt like that's not what we do in statistics. We kind of have a more central process of admission. But the world of research is like, of course, full of opportunity. You can definitely keep emailing people to see if they can work with you. And somehow, interestingly, with everything going online, the opportunities have opened up that you do not actually need to travel like to be able to work with someone. Like I can tell like this was not even a possibility like maybe even 2 years ago. No one would even entertain if you say that, okay, you do want to work with someone remotely. But now I think it's also beneficial for both sides. Like you can have these opportunities, at least get some reading on, and then that can help your, maybe you're building a CV. You can say that, okay, I did work on something, and then you can say that, okay, you want to pitch it in for your research agenda, in the sense that when you write research statement for application, that might be able to, I mean, boost your chances. Anyway, so enough of that introduction. So talking about dependence, like the time series is like a recorded data of like different time points. Like you observe some data. Let's say you look at electricity consumption in different months of a particular city, or like of a particular household. You can look at like some production over time points. So these data sets are called like dependence, like a temporal dependence, because temporal is coming from the time stem, the word time. And these sort of temporal dependence is what we try to capture in time series analysis. Now, the dependence does not necessarily have to be over time. The data set does not have to be necessarily over time. It can be over like spatial, it can be like some sort of network and things like that. And typically the statistics literature, whenever you try to write a research paper, you actually have to get some sort of data. I mean, this is a paper from GRSSB, I think the topmost statistics journal that you can write a paper on. And even in that paper, people try to sort of ignore the dependence. They try to write that, okay, uh, we can assume that it is independent and go on. But in real life, nothing is really independent as such. There are some sort of dependence. I mean, direct dependence, there could be some causal dependence in the sense that some external variable might be affecting both of them and things like that. So it is important to assess dependence. So this is just like an excerpt from one of the paper. And you can see here they did talk about, in our analysis, we ignored the dependence of the p-values, which is a moderately risky assumption for the prostate data. So even after admitting that it is indeed moderately risky, it did went ahead and it did go ahead and like work with just assuming independence. So time series data actually tries to address this problem and tries to see if you can, I mean, in a systematic way, if you can address this, build a good model, and then show that why addressing the dependence was important. So in this talk, what we will do is we will talk about time series applications, some motivation, some very basics of time series, like whenever you see a data, what sort of things you can do just to say that, okay, indeed it is like a time series, and we should not just treat them as like independent replicates. Some popular time series models like autoregressive process, moving average process, ARMA process, archcars. These are very technical. I won't spend a lot of time, because if you understand the basic motivation, you can always go and read up these quantities, like read up these terms. The spectral density is something that we use. It's a little bit detour from what we do here. Like here we are working in the time domain, and then here we'll be working in the frequency domain. I will talk a little bit about time varying models. That's like, I mean, I'll go a little bit deep into one of the specific research topic that I've tried to address so far, and talk about an important application of, I mean, time series. It's sometimes whenever you write a paper on time series, they will say that, okay, I understand that you're trying to analyze the past. What about the future? People do want to know future. People do want to see where exactly a particular equity or a stock or some number, production, or anything, any real time series that you talk about, people do want to know what's going to happen in the future. Let's say weather variable. Like, so today, like here it's raining so much here, and like I did not check the weather initially. I thought I will be able to go to the department and give this talk, but then I realized like late last night that, okay, it is raining. But if I were like looking at the weather variable, just type like Gainesville weather, you will be able to see number of days, and it is true for any region that you can look at. You'll be able to see like number of days, even by hours. Of course, these forecasts are always not true, but typically they try to bring in the factors like what part of, like what time of the year this is in, and then last year what was the temperature on that day, unlike recently what's been going on. So, and then the forecasting is indeed very important. Like if you're trying to plan something for the next weekend, then you would want to know like whether it will be rainy or sunny, or like what sort of weather there is. So that's why forecasting is indeed like quite an important component of time series analysis. And then finally, I hope I will have like 5 minutes of time. I'll just talk about a little bit in terms of like how you can extend the ideas from time series to explore dependence in spatial network. Like you observe some data over a matrix, or like you observe data over like a social network or some sort of network, and how you can extend it to this sort of scenario. So this is just a basic definition. Time series is just a collection. I mean, I've already mentioned this, collection of observations that are made sequentially through time. We will focus on discrete time series here, in the sense that we will be having exact timestamps, and we will be, I mean, we will just, for the sake of simplicity, we will assume that we are collecting data on every regularly, I mean, on every regular interval, in the sense it could be every day of the week, it could be every week, it could be every month, it could be every year. So these are like the discretized time points and not over a continuous time series. There are quite a bit of work on continuous time series as well, require some sort of different modeling, but usually every data that you see, we will always discretize. And that's why I want to focus on this discretized time series, where you have an actual timestamp on where these data are collected. It could be possible that you can see a data where there are like for time, some timestamps, there is no data and it could be irregular time interval. But I will not go into those sort of pathological scenario. I mean, it's possible to extend there quite a bit of work where data are observed over irregular time intervals. We will not go into that. So some of the applications, as I was already mentioning, it could be like agricultural data, crop production, how crop prices are changing, business and economics. This is something that I have been like doing for constantly for a while. The area of econometrics, where you look at this sort of stock prices, interest rates, forex rates. This is that. This should be rates. Then monthly price indices, quarterly sales, yearly earnings, and so on. Then you can have like some engineering and like some medical data where you have like sort of EEG type of data. So these are observed over time. Recently, I've been like trying to work on something called like an fMRI data, where you observe these brain cells, but then these brain cells are observed over like a period of time at every visit. So we are trying to see how the signals, there's something called a BOLD signal, the bold signal is changing over time. So that sort of applications are coming from this, emanating from medical data. In terms of like climate variables, there could be temperature, rainfall, wind speed, and even outside that, social science, there is like birth rate, mortality rate, crime rate, COVID-19 progression, like how the number of cases are going up. So there's like a lot of data that you see around you. Actually, if you keep collecting those sort of data, it can give rise to some interesting time series. So there are many applications that you can think where time series can be interesting, and it is important to understand how the dependence is found, like how to model this sort of dependence, and then how to incorporate that to make some sort of meaningful analysis, to understand how the trends have been in the past, and then to assess the future, like how the future is going to look like. So some pictorial examples. I choose to give like some pictorial examples here, just so that you understand how the data progression happens, and then based on that, what sort of interesting questions you can answer, or like you can even ask. So this is like a hat crude data, temperature data. So average temperature data, northern hemisphere, southern hemisphere, and the global average temperature. As you can see clearly, I mean, the temperatures have been rising pretty much in the last 50 years. I mean, from 1980 on, you can see, I mean, of course, you can ask like why the average is at zero. So this is actually normalized or like subtracted from the 1860 to 1900 average, or in at the Greenwich time. So like at the central UK location, whatever was the average from the 1860 to 1890, people have subtracted that and then looked at this average temperature. So clearly, once you set a baseline, you can see there has been some sort of change around this Second World War, and after that, it's been like steadily rising no matter which hemisphere you are looking at. And you can see like the amount of change is also changing, like in the sense it's going up pretty rapidly compared to like how it was before that. So there were like sort of, there were trends of going up, but then after that it went down, and then again it below remained below this standard of zero. But then suddenly now, if you look at this sort of numbers, the next question could be, could you predict what is going to happen in the next 20 years? You can see the years are given here in like 20-year intervals. So we are already at 2020, this is old data, but then you can try to understand where we have like, where are we heading at 2040 and things like that. So these sort of questions can be answered. Like here you are seeing two time series. Of course, this global is average of these two, but the two time series co-moving together. So as you can see, northern hemisphere had a much rapid rate of increase than the southern hemisphere. So an interesting question could be, why exactly is this happening? Is it because of some other geographical variables? Is it because of the different policy, different rate of industrialization, and things like that? So these sort of questions are like important socioeconomic questions that you can ask, even just from looking at a very simple like average temperature data like this. Then here you can see the population change, like the population change data based on like three different net migration, the total change, and natural change. As you can see, this is also data over time, like you are observing it at every 5 years, and then three series are moving together. So you would be interested to understand which series are going up, which series are going down, and how they are affecting each other. So the basic goals that are there, like based on these sort of examples, is that how can we find a natural trend? Like, can we talk about, can there be like a seasonal trend, a temporal trend, or a spatial trend? So for example, as I was mentioning that here, usually in Gainesville, there's like quite a bit of rain. And usually it's a very interesting thing that happens is like it always rains around like afternoon. And I've never seen, like when I was in Chicago, I've never seen this pattern. Like there's like a consistent afternoon rain that happens in Gainesville in the month of like say August to September, October. And I was a little surprised, why is that happening? So, and this can be explained, like I am not making it up in the sense that you can always go back and look at historical weather data and try to see that it is raining around that time. So that means there is some other geographical variables that's affecting that sort of pattern. And there is some sort of seasonality in this, because every year, August to October, if you are seeing something, that means that time of the year, there is a periodic seasonal component. There is, of course, a temporal component in the sense some years are warmer than some other years, some years are cooler than that. So that means there is like a temporal pattern. A spatial pattern would be like if you look at a few cities together, say that in the context of temperature data, how they are moving together and like how trends in one city is going to affect the others. Then we can talk about the general mean, how the variability is changing. So as the variability changing, if you just refer back to the last picture I was showing, the variability in the northern hemisphere was much larger than the variability in the southern hemisphere. Now, coming to the next part, which is more important in terms of understanding the future, can we do some sort of sequential analysis in the sense based on this observation, can we know like what is going to happen in the immediate future, so that if we know that it's going to go like that, if the temperature is going above, then we understand the reasons behind it and we might take some mitigating strategies and things like that. And then the forecasting, as I said, like forecasting is super important. No matter what sort of time series data you give, people would always want to see where the future is, and there could be number of motivations for why forecasting is important. Now, for example, this is why forecasting is important. This is like when Uber was starting, and this is back in 2013. And as you can see, the number of ridership was going up every month. This is at the very beginning of Uber, when Uber became popular. Uber actually started a lot earlier than this, but Uber started becoming popular around this time. And so if you are standing here, a natural question from like Uber's management team would be to understand how ridership is going to go up. You can think about like in a particular city or something like that, so that they can have more drivers that can manage that sort of demand. And can you be able to see like what will happen here? Like these are actual data, and in this data, as you can see, it's like there are spikes, but overall trend is going up. So based on that, then you can take a decision on how to allocate more resources so that you can manage an increasing demand. So things like that can happen. Like you would want to know what is going to happen in the next day. You would want to know what is going to happen in the next 1 week, 1 month, or so on. So typically what you can do here is you can try to predict what's going to happen in the next few days, or like total number of riders that you are going to see in the next 1 month. And then you can build like a confidence interval or a prediction interval for that. And based on that, if you would understand, okay, this is where the numbers are, but this is of course a random variable. No one knows until it actually happens. So then you would want to actually control the variability. Like you are making a prediction, any prediction cannot be exactly correct. Whenever you are making a prediction, and this is also important as like a statistician, whenever you are estimating something or predicting something, you cannot just say that this is one single estimate that I have. So I have a question. This is continuous time series. Actually, Onkan, I think that's a good question, but it looks continuous, but usually you do it on like every time day and then you just stitch them together. So it is not actually continuous time series. Even if I join them together and it looks like a continuous line, it is still discretized over maybe each day. This is each day stitched up together, and that is why you see like this sort of spikes. Otherwise, you'd probably not see this sort of spikes. But I mean, any time series that I'm talking here are like actually discretized time series. It is, of course, the temperature data. You can talk about temperature data. Temperature data can be continuous. Like you can talk about temperature at any point of time. But imagine like whenever you are looking at the future temperature, you are always actually looking at what is going to happen at 8 o'clock, 8:30. You don't look at what is going to happen at 8:31, 47 seconds and things like that. So the data you collect is actually discretized, and it could be like a final level or like a more coarser level, but it's usually typically discretized. So this is actually discretized data. Now, coming to the basics, like how do you really understand? Like I give you a data set observed over time. How do you understand whether there is a correlation going on or not? So the very basic definition is easy in the sense that the autocorrelation is defined as correlation at lag h, and at lag h, gamma h is expected value of xt plus h minus expected value of xt times expected value of xt plus h, which is just the covariance of xt and xt plus h. And this is auto covariance. You divide by gamma 0 just to make it the auto correlation. So you can see the correlations are going down here in the sense that this is one paper that I recently wrote about like time series classifier. We were trying to understand whether between malware and like there were some attacks on like some hardware security, and some of them could be malware and some of them could be benign. We were trying to design something that when something new comes, we'll be able to classify into one of this. And what we did was we had like quite a few actual data sets, and then we looked at these data sets over time. Now, so far, like even this is 2021, like this paper was written in 2021, people have been using only independent data. And we thought, okay, why don't we try to do like time series classifiers and things like that? And we were able to beat the existing results by quite some margin. But even before doing that, while motivating, like why even looking at time series makes sense, we were looking at these sort of counts or scores that you can get like whenever a new application is downloaded. And like it's not, I'm not going into the nitty-gritty details of the actual numbers. Once you have a data over time, you can always look at the auto correlation like this, and I am plotting here the correlations. And as you can see, the correlations indeed are quite a bit high. The correlations are going down eventually. That means if you're looking at 0 and lag 10, at lag 10 the correlation is not that significant. So time series always have this interesting pattern, is that if you observe things over like a like over like quite a bit of lagged interval, things start becoming more independent, and they start behaving more independently. And that's what you see here, in the sense that the correlation indeed goes pretty down, like pretty, like this blue line is the line of significance. If it's above that, you say it's significant, otherwise you say it's not significant. So for the malware data, you see it was dying down pretty fast, but for benign data, somehow the correlations were very consistent, very persistent. And indeed, like even at lag 10 or lag 15, the correlation was indeed there. And so this is like just from one real data set, but any time series data, you can look at the correlation. Based on the structure of the correlation, you would understand what sort of model you would want to take for modeling that time series. And if you want to statistically test, there are ways to test that. Like you can do like a Darwin-Watson test statistic. And this Darwin-Watson test statistics formally tests whether indeed there is a correlation or not. I mean, if there is a correlation, this test statistic will give you a value away from 2. If there is no correlation, it will be close to 2. And we indeed showed that, I mean, the p-values were indeed pretty low, showing that, okay, most of these data sets indeed were showing significant correlation. So now coming to like some very basic models, I'll probably only be talking about the autoregressive model. So autoregressive model, as the name suggests, it's auto regression. So your data yi, or the ith time point, whatever you observe at the ith time point, depends on what you observe on the I minus 1th time point. And so that's why we call it autoregressive, as in it is getting regressed on its own lagged values. So similarly, you can build onto that, and like you have like moving average process, ARMA process, and things like that. So what exactly is an autoregressive process? The autoregressive process where you look at a data point at ith time interval, yi. Yi is rho 1, yi minus 1 plus ei.
Professor,
Yes, sorry.
really sorry to interrupt. There was a question in chat.
Yeah,
The
I'm
question was,
sorry.
is autocorrelation the same as serial correlation?
Autocorrelation is indeed same as serial correlation. Yes, I mean people do use that like this sort of term. It's a serial correlation is indeed autocorrelation, and I mean autocorrelation is more like a formal term. Serial correlation is if there is some sort of autocorrelation, they say okay, there is a problem of serial correlation. And there's another question. I think these are direct messages. I'm sorry, it does pop up here. Is it correlation over time? It is indeed correlation over time. So yi being correlated with yi minus 1, and then so the plot that I showed here and the plot that I showed here, these are correlation over time. In the sense, what does this number signify? This number says that if I'm looking at yi and yi minus 1 at lag 1, this is the correlation that I'm expecting. So indeed, it is correlation over time. You can look at yi and yi minus 5, and this lag 5 number can give you some idea how these numbers are moving. So coming back to the autoregressive process, it's called autoregressive. As I mentioned, yi is being regressed on yi minus 1. What does that mean? That means that if you give me the value of yi minus 1, the best possible guess that I can make about yi is probably rho 1 times yi minus 1. But of course, it's a random variable, so it won't be exactly rho 1 times yi minus 1, but we will be adding some component, the EI part. And this EI part, technically, you can assume that this EI part is like IID. Now, if rho 1 is very, very small, that means yi becomes reduced to EI, and EI is IID, EI is like independent, there is no dependence. So based on the simple, like this simple model can give you a very good introduction to time series in the sense that based on the value of rho 1, if rho 1 is very close to 0 or like exactly 0, see yi becomes exactly EI. Or even if it's very close to 0, then yi becomes close to EI plus some small perturbation from the past. But if rho 1 becomes bigger, I mean, rho 1 becomes close to 1 or minus 1, then you know that yi indeed depends on yi minus 1 in a significant way. Then you can have models like yi being ei plus theta 1, ei minus 1, in the sense that yi is not directly dependent on yi minus 1, but there is an IID process going on over ei. And then using those EIs, you can like sort of stitch together the EIs to make your yi. You can combine these two to bring like an autoregressive moving average process, and then go on like building this sort of model. So for financial data sets, uh, rho 1, what is that? So rho 1 is a coefficient, like it determines how yi is going to depend on yi minus 1. So yi determines like yi and yi minus 1. I think one good thing is like you can probably ask the question, like people are coming to the chat, maybe it's good like you can ask the question to everyone. I mean, like just make it like a live session where you raise your hand and ask a question rather than direct message. What happens is if I want to type something, it directly otherwise goes to the direct message. Just type the chat to everyone. Everyone else will also benefit from a question that you might ask. So yi equals rho 1, yi minus 1.
Yeah, I have
Sorry.
changed the setting to chat to everyone. And before
Okay.
there's a raised hand I see. Hari, could you unmute?
Yeah, Hari. Yes.
Hi, sir. Sir, can you go to the previous slide, please?
Yes.
The previous one, yes, in this graph. So can we assume independence for a BI malware data? Or is it also concerning to make that assumption when dealing with data sets which have the diagram similar to BI malware or BM malware?
Right. So as you can see, of course, the dependence is not that strong here, but still, if you look at dependence at lag 1, it is above the line of significance. So indeed, it is like an autoregressive 1 type of process with this sort of dependence. So I don't think you can still just go ahead and say that, okay, this is dependent. If all these numbers were below this line, then probably it was safe to assume independence. So that is why what we do is like we just do a very basic check. We just plot the ACF just to understand whether where these coefficients are lying, and if they are like, if any one or two of them are lying above, as you can see here, probably it was not that high as like this one, but there is still some sort of persistent. Like if it was like just this one and everything went down, you could have probably made a case saying that, okay, we might ignore the lag one dependence. But like here also you can see there is some sort of persistence, right? So that's why for this one, I don't think you can do it. Maybe for this one, you can just treat that as ID data. It's kind of a subjective call, but so that's what I said. When I have a ACF plot, it's a subjective call that what you want to do. If you want to formally test it, you can take help of like Darwin-Watson test, like you have an actual p-value, and then you can take a call.
Okay, thank you.
Yeah, thanks for asking. So then we build on to that, and we go much larger, like we go like Arch and Garch. Of course, these models are, it looks a little bit tricky, but typically these are the models that are used to model these financial data sets. And even to this date now, like so many neural network models have shown up, in the sense that no one actually falling back onto Arch and Garch. I mean, it still has quite a bit of value in the econometric literature. We are able to publish quite a bit of papers on Arch and Garch consistently. But if you are working for like a hedge fund company, and quite a few of my friends do, they are like putting everything into neural networks to build these predictive models. But these Arch and Garch models are still somewhat important to understand the dynamics. Like the person who created Arch, Robert Engel, he got a Nobel Prize just to create this model, like this Arch model. So just introduction of this model back in 1982 gave him a Nobel Prize in 2003 in the economics. So that's probably, I mean, enough to convince that these models are indeed still important. Even nowadays, there are so many neural network models that are probably getting better forecasting results. These still have some value in the econometric literature. Anyway, so the idea is like you look at the ACF and PACF plot. I'm glad like Hari asked that question, because based on the ACF and PACF plot, it directly gives you a suggestion how to decide on what sort of AR process you should go for, what sort of MA process you should go for, and things like that. So this is like a chicken price data. It's a very sort of preliminary data where you look at the like price of chicken. And as you can see, the price of chicken is going up. There is some sort of periodicity, in the sense it goes up, it goes down, it goes up, it goes down, it goes up, and so on. So as you can see, there is a linear trend, like a trend is going on. I mean, it is increasing over time from like 2000 to 2015. And we would want to see, like, if I just look at this data and then we will plot the ACF function. Say I collect this data every week or every month, and if I plot the ACF function, whether we'll be able to spot this data, like spot this sort of correlation or not, or whether I can somehow use that data to understand that there is a seasonal component, there is a periodic component, and things like that. So I would say you can try the ASTSA package from the Shamoy-Stoffer book. That Shamoy-Stoffer book is it's openly available book, and this book actually gives a nice introduction to how to understand this ACF function, and it also gives you some basic R codes that you can try. R is a freely available software, so anyone can try, and that will give you some insights about how to understand different components of the model. So coming to this sort of periodic nature, like when you see a periodicity, sometimes we actually use like a spectral density. This is in the frequency domain. So in frequency domain, indeed, instead of looking at just one numbers like x1, x2, x3, and so on, you would want to understand if there are some periods, like in the sense if there is a seasonal period, if there's a weekly period, monthly period, yearly period, and so on. So for that, what you do is based on a data. So this is close to, if you have done like some classes on Fourier analysis, you'd probably understand, or you'd probably be able to like sort of appreciate that. Like given one data, you know, gamma h, I define gamma h. Based on gamma h, you can go to Fourier at frequency omega. And then from frequency omega, if you know the f of omega for every omega, then you actually know the entire time series, because this f of omega can be retrieved via a function like this. So this is very in parallel with what we learned about this Fourier analysis and retrieving an actual sequence based from its Fourier analog and things like that. So this spectral density is also somewhat important in the sense that sometimes we can't do everything on time domain, but we have to do it on this periodic domain. So when we look at data like this chicken price data, we want to understand whether there is a periodic pattern of 5 years. Like, of course, if you say there's a seasonal pattern of every year, I mean, usually, so this is chicken price data. I can talk about gasoline price data. These are from personal experiences. Like gas price data, it goes up in the, it goes down in the winter and then it goes up again. So there is always a very obvious seasonal pattern. But what we want to see is over the years, do we still have another periodic pattern? So here you can see we do have a periodic pattern of every 5 years when it goes up and then it goes down. So this spectral density actually allows us to understand what are the different periodic components that are important. So for example, if you look at this chicken price data and you feed it in, you will see there is a peak here, and then there is a peak here, there is a small peak here, and things like that. So that will tell you, like, if you do 1 over omega, that can give you like the periodic, like the length of the period. So here there is a period around like 0.2, so that means 1 over 0.2, so about like 5 to 10 years there is a period, and there is an obvious yearly period which is 1 over 1 and things like that. So this sort of spectral density helps us. This is called, like, these pictures are called periodogram, but spectral density sometimes helps us to understand if there are like multiple such periods. Again, these are again very technical ways, like these are some of the very basic things that you can do when you come across a time series data, and that can give you an idea what is a good model. Then you can fit that sort of model, and then you can do inference about like what exactly is row one, what is the significance, how would you understand like if this is a explainable model and things like that. Now, this is what I will like sort of not go a lot deep into this, because this is a little bit more technical. This is more into what I do as like a researcher. But since that was a basic introduction, I thought in this talk I'll also give you just a brief overview of what we try to do. So what we try to do is we try to sequentially build from the idea of independence, and then we try to see if we can build a very general model how to understand this very general time series, where the dependence could be like many things. Like, we do not want to fix ourselves on one particular model. Rather, what we want to do is we want to build a general theory for like general time series, and then we want to see how exactly our model would fit into those scenarios. So what I was trying to say, like, if you have you have looked at these EIs that we had in this previous slides. So what we typically do is we assume these EIs are like IID, there is no dependence. And then we can like just combine them, like, so EI plus EI minus 1, EI plus half EI minus 1, and so on. Even just a simple series like that becomes dependent because the EIs are shared across like neighboring epsilon I. Then what you can do is then you can build a little bit more, generalize this linear structure to a more non-linear structure. Like, you can think about fancy structures like EI plus square root of 3 EI minus 1 times EI minus 2. Even just a product of these two, EI, if you just write epsilon I as EI times EI minus 1, that becomes a non-linear time series. Then you can think about, okay, how can I change this fi, like this f I can change at every point of time. Like, I can make, like, say instead of square root of 3, this could be changing like what sort of coefficient you give at every point of time. Then you can have multiple series like that picture that I had about temperature, and you would want to see how each of these series are moving together. So that's kind of like a general path of how we try to like sort of sequentially generalize from IID data or univariate data to a very general multiple nonlinear time series. So I worked with Professor Wu back in like Chicago, and he was my PhD advisor. So he created this functional dependence measure that kind of extracts these AI analogs, in the sense that, see, this structure is very easy, like to do math on this sort of structure is comparatively easy. But when you actually destroy the structure to make it more general like F, it is important how you can extract these coefficients in some way or form. So he has like this sort of measure that allows you to extract these features. These are again very technical thing, not that important. But this is something that we like sort of sequentially build. We are able to get theoretical results, and then we fix on some model. Like we say, okay, we have results for general theory here, but for this Sarajevo model, these will be the assumptions. And then under these assumptions, we can have this nice estimation results. Now, coming to this time varying model, like one of my basic research focus is on time varying model. So what exactly is a time varying model? And a time series naturally is time varying because there is quite a bit of variance, like quite a bit of variability that you see over time. So this is a data daily new cases in the United States. And this is in the very beginning of when the cases started coming up last year. As you can see, the trends are going up and then it's going down. And it again went up quite a bit since September. And it went down, again went up in the summer and so on. So these trends are changing over time. And of course, it's difficult to model time series like that just by the very simplistic models that I showed there, like yi equals rho 1, yi minus 1 plus ei. Because if yi equals always rho 1, yi minus 1 plus ei, then you would expect a same pattern consistently throughout the time series. It won't show going up, down at different level. Like here you can see there was a slope here, the slope is different here. It kind of plateaued down a little bit here, but then it plateaued down quite a bit here. So a single model, a single simplistic model like yi equals rho 1, yi minus 1 plus ei might not actually cut it. So there are data like this is Bitcoin data from 2017. As you can see, Bitcoin was like pretty slow. And then suddenly, like from the mid 2017, it went down. Then what happened was it went down to 9,000, it was around 16,000. And now again, it went up to 60,000 and so this sort of data, like it is very difficult when you look at this sort of data, just to say we have one model like yi equals rho yi minus 1 plus ei to explain this. It won't do a good job. Of course, people have tried to do that, like they try to dissect the data, like sort of divide the data in different small sectors and then try to do that. But it's again, it becomes a little subjective, something that we should avoid. Like this is what I believe as a statistician, is that we should not do something that is very subjective. Of course, we will use our expert knowledge, like we will use like some sort of insights, what sort of variables could be important, but your analysis should always sort of preach objectivity, in the sense that if I say divide it into like every week or every month, then someone might come and ask like, how do you decide on that? Like, why not like 3 months, 4 months and things like that? So your model should be adaptive to this sort of like subjectivity and make it more objective as such. So these models, we wanted to look at what would be like a time varying model, like what sort of time varying model do we look at. So this slide will give you an idea what exactly we are doing. So the very simple model, this is what we call like time constant models, in the sense that yi is just one constant number plus ei. Yi is a linear regression xi prime beta plus ei. Yi is square root of, this is this arch-garch type of model, a0 plus a1. Note that all these models are stationary models, in the sense that if I know yi minus 1, I would have a good guess of yi, provided I know my a0 and a1. Same as like beta and g. But these are stationary in the sense these are always like stationary in a local sense. But if you have a long progression of data, it's very difficult to say that a single G or a single beta or a single set of A0 and A1 will be able to model the entire thing. So analogously, we try to build like sort of a time varying analog of these. What we do is we keep the basic structure, but we change the parameters G to G of I over N. We change the parameter beta to beta of I over N. We change the parameter A0 and A1 to the like functions of time. And then once we do something like that, what we can do is we can estimate these trend functions themselves as function of time rather than just estimating one constant. So that instills some sort of objectivity in how you would want to model that. So what we are doing here is we are still sticking to those simplistic models, but instead of sticking to a very simple model, just one single rho one, I am now changing my rho one constant to a functional value, like a function of time. And then I will estimate this coefficient not just as one single number, but as an entire trend function. So that will do, like, of course, that gives me some objectivity in how to model it, but I will also be able to understand how this function g is changing over time, how this effect, like the beta, if in an usual regression model, beta is always the effect of a certain covariate. So we'll be able to understand how these covariate vectors beta would be changing over time and things like that. So this sort of model, like this sort of time varying model, is something that I spent quite some time on during my PhD and maybe the immediate next 2 years after that. So I am not going to any theorems and things like that, but what we want to show here is this is the USD GBP conversion rate data. You can see there's quite a bit of volatility here in the beginning of 1990 to 92. Then the volatility went a little bit down. So we fit a model like this sort of arch type of model. And we did show that A0 was indeed quite a bit of volatile. The volatility went down. So this is kind of consistent with these more spikes here. But when it came to A1, like the dependence on yi and yi minus 1, it was okay, but you can still probably fit like a line here. So these red lines here are like the estimate of these functions A0 and A1. But as I mentioned, like in statistics, whenever you estimate something, your estimates do not stand alone unless you give a confidence band or an error estimation band. So just a very basic strategy of how we do this, like say this is the line you are trying to estimate. What you do is you first draw like your basic estimate. That was the red lines that you saw there. And then you do is like, then you try to create a sort of a Gaussian analog of that, in the sense that something that you can keep recreating, and this Gaussian process is created from the data. And then once this becomes simulable, like you can keep simulating these sort of black lines many times, and then you can look at the boundaries at every point. So then you see these boundaries indeed cover the initial blue line. So that is what we talk about. That is what we do in simultaneous confidence interval. These black boundaries are called a simultaneous confidence bands. Once you see these bands, that can give you more idea about where exactly this number would be. Otherwise, if you just stick yourself to this red line, see, red line is just an estimate. So this is important, like as a statistics class, like, I mean, in a statistics class, an estimate is not enough, like ever, like an estimate does not stand alone. So whenever you give an estimate, you also have to give me some sort of error quantification, uncertainty quantification. Once you have this band, then you know, even if your estimate was missing something, at least it should be within this line with 95% confidence. And then you can see that, okay, I can fit like lines, linear lines here. So maybe now I can go back and simplify those G of I over N and things like that, and give me more interpretable, more summarized model. So that is the goal of doing some sort of time varying models and inference on that. We then went ahead and did something on this count value time series with the motivation of analyzing the daily COVID count data. And what we wanted to see was, this is like, again, I would not go into the theoretical details, but as you see, like how we use the very simple time series model to sort of go back and reflect on what sort of physical significance this data could have. Like if you remember last year when the COVID-19 started becoming, I mean, everyone started knowing about it, they talked about like this incubation period. Like if you are actually coming across someone who has COVID, you won't be showing symptoms right like in 3 days. Maybe in the next 2 to 3 days, 4 days, you do have like an incubation period. So what we wanted to see in this data was that, if I just treat that as an autoregressive process with this A1, A2, A3, A4 being the coefficients of like lag 1, lag 2, lag 3, lag 4, can we show that indeed these data, these AI coefficients have significant lags when you are going at like lag 6 or lag 7? So we were indeed able to show that. I mean, I do not have the picture for that, but we were able to show that indeed the lag 6 and lag 7, those coefficients became very significant. It could be due to a weekend effect as well. In the weekend, there are less number of cases, and that could be, so we did explain like how a very simple autoregressive model can still throw some light on how these data sets are progressing. Then we can have like trend cycle model, as I mentioned, this sort of climate data. This is the previous data that I showed, and then people can fit like this sort of. So as you can see, this is like the average line, and then they have this confidence interval. So this confidence interval gives you a good idea about the increasing trend here. And usually for climate data, again, this is something that I also knew when I started doing this research. Of course, if you're looking at average temperature over, let's say, quarters, like, so there are 4 quarters in a year. So the natural period length would be 4. But if you're looking data at an annual scale, then usually there is a period of like 60 to 70 years. And that's what people typically have observed, at least for temperature data. Our analyses were also consistent with that. Then finally, a classic chessboard problem. So this is like a little bit of theoretical problem, but I don't want to go into that. But if you remove this, everyone probably in the CMI community knows this problem, that if you remove 2 ends, you can't cover this with 31 dominoes, even though there are indeed 62 things, because a problem in invariance happens like that. There are, if you cut out 2 whites, then there are 30 whites and 32 blacks. So you won't be able to cover it with a domino, where domino always cuts like 1 black and 1 white. But what is statistical invariance? So usually statistical invariance, this is not how we are usually taught, like the central limit theorem and things like that. But central limit theorem indeed is an invariance principle. What that says is that if you have any data, and if you understand, like if they are IID and mean 0 and finite variance, then their summation over root n actually goes to normal 0 sigma square. So why do I call it an invariance principle? Because like it does not actually depend where this data is coming from. So this sort of central limit theorem is key to do many, like I think it's one of the fundamental pillars of statistics. But of course, the natural question is that if you relax that, what happens for time series data? Like for time series data, would you still have something like that? Indeed, we still have something like that. And that is what was my first project with my advisor. It's a little bit technical, but it does say that indeed Sn over root n will go to normal 0 sigma square. Not only that, every partial sums, like x1 to x1, let's say n is 100. So I'm not saying that x1 plus x2 plus x100 over 10 would go to a normal distribution. We would also be able to say every possible partial sum. We don't have to go that far. Every possible partial sum would still kind of converge to a normal distribution. And these sort of results are kind of crucial in what we showed earlier. Like when we were building those black lines were built because we have some invariance principle like this. So no matter where the data is coming from, I can always create a black line that is some sort of Gaussian process. And once we have the Gaussian process in hand, we can keep creating that. We can keep creating many black lines and then keep getting the boundaries. So if you think about it, it is kind of similar how you do these confidence intervals. If you have taken any introductory statistics class, the confidence interval for a mu parameter or sigma parameter is also done by that. Like root 10 times x bar minus mu goes to normal 0, 1, and we use that to create confidence interval for mu. But what we are actually saying is, okay, x bar minus mu is close to a normal distribution. And then we know if we create many copies of this normal distribution, then we can look at their boundaries, and those boundaries can give me a confidence interval for mu. So same type of strategy is being adopted for that. only in a more complicated or a more time varying model type of scenario. And we needed some more advanced tools like that. Please. And then finally, I think I will be able to wrap up in like the next 5 minutes or so. Some interesting applications that we do is like change point. As I mentioned, if you are observing data over time, sometimes there are like abrupt intervention. You would want to see when are these interventions happening. Like if you're looking at the past data, you would want to see, okay, these are the 2 points where there was an abrupt change. Why did that abrupt change happen? Like, is it some external force? Was it there was a chance, some sort of policy change and things like that? What are the external factors that are motivating here? Here you can see we were looking at like a genetics data, and then this gene data, we were grouping the genes based on where they observed this change point, and then we can see that the breakpoints are happening, where exactly the breakpoints are happening are kind of have a clusterized structure in them. So these sort of problems, I do work on like change point problems in time series. And there are interesting things that you can think about, like, okay, I have a change point in one time series. Can I take another closely related time series and see how the change points are synchronized or not? If the change points are far apart from each other and things like that. How many, like, can we have like multiple change points and things like that? So change point problem is like a complete separate literature on its own, and people work on different change point problems even outside time series. But for time series people, change point indeed remains an interesting topic. And as I keep mentioning, forecasting remains and one of the most important goal. One of my recent paper that was just accepted, it was in a linear regression model and a high dimensional linear regression model. What if I want to predict yn plus 1 to yn plus n? I mean, I do want to predict that, but there are some external factors as well. So in this paper, we kind of were able to integrate some of the existing literature, some of the knowledge we have from high dimensional regression, and some of the knowledge from non-parametric quantile-based estimation for the future aggregated data points. And we were able to aggregate this to predict what is going to happen in the next few days. So it's like not predicting yn plus 10. We are instead predicting like what is going to happen in like yn plus 1 to yn plus 10, like in an aggregated fashion. So these type of problems are called like short-term and long-term forecasting. There are many other applications, and I'm like almost done. So this is what this is like I think this is from LA or some neighborhood of LA. Like in California, there's quite a bit of fire problem, in the sense that there's quite a bit of, like, every year there's some sort of fire problem, and forest fire is very common there. And people do look at this sort of spatial grid just to see, like, just look at the satellite image and how they change over time, to understand whether there is like a problem of like some incumbent, like, or some impending fire that might be happening. So they have past data when how this data set, like how these images look like right before the fire. So based on that, what they're trying to do is they're trying to train their model to understand, okay, can we predict if it's getting too close to like a forest fire? And this is true. Like if you actually go to any sort of national park and things like that, if you search in Google, they also pop up. Look, if I have seen that happening in the West Coast, like different parts of West Coast. When you type that, they would give you a forest fire prediction as well. Like, okay, we have like 10% a chance of a forest fire prediction. We have a 50% chance of a forest fire prediction, and so on. So these sort of problems are important problems where people are regularly using time series without actually understanding that time series is being used. And then finally, as I mentioned, there is something called like a network dependence, where, like that you have quite a few data points where they are like closely related to each other, and people are working on like whether the dynamic they are changing, their connectivity is changing over times and all. So I was recently looking at this paper. It's that the cryptocurrency network suddenly, like in the last 3-4 years, became more interconnected than before. Like they were moving more independently earlier, but suddenly now they are starting to move more coherently. If one of them goes up, the others are going up. And it is true. Like if you personally follow one of few of these things, you will understand what is going on and like this sort of results. So there are quite a bit of scope in analyzing this sort of data. A large number of data that we analyze are actually publicly available data set, and I do put an emphasis on that. Like if you are like waiting to get like survey data, that means you are already like waiting quite a bit of time to get survey data. Survey data does take time. So I do put an emphasis myself to make sure that the data we work on is like the publicly available time series data. And you would be surprised to know how many natural resources we have for these sort of data sets. And that's pretty much it that I wanted to talk about. One last slide I have. This is completely very different from what I usually do, but it's an interesting collaboration that we started working on. And you probably know I have a collaborator on it with, and he was a CMI alumni, by the way. And back in like I think he studied physics there, but he now then shifted to this world of deep learning, and we have been looking at some of these interesting models. So RMS Prop and this Adam, these are very popular neural net training algorithm. You might be wondering, why am I talking about it? Like, I mean, what does a neural net algorithm to do with like this sort of time series analysis? And Adam, by the way, is like, it came out in 2015. It already got 70,000 citations in 5 years. So it's world's one of the most cited, like one of the most popular paper that has come out. Interestingly, by the way, when the paper was proposed, there was a mistake in that. And like in 2018, actually someone from Indian origin, they actually corrected it. And that paper also got very popular in 3 years from 2018. So there's a, like, this is something that I've been doing very recently, this neural network. The reason being, if you look at this type of algorithms, this type of algorithm also hinges upon what happens in the previous step. In the sense, this Adam algorithm, it has xt plus 1 equals xt minus this thing times mt. And then these mt's are all time series as such. Like the if you can relate to like the things that I talked about in this class, in this lecture. But so looking at this, what I felt was that, okay, I mean, if these sort of algorithms are doing so good, like it is getting such great results, maybe we can use some of the theory that we know for autoregressive processes to be able to like we will be able to incorporate them here and establish some interesting results. Like even though Adam and RMS Prop are out there for a while, and then there are so many citations, there are quite a bit of theoretical guarantee results that are still open, and people have not been using this. And people have been focused more on, of course, the applied side of it. They are applying these algorithms. They're proposing the variants that can like help you scale up to optimize huge problems. I mean, like problems with huge data sets. But somehow the very basic questions is that, like, how do you know that this will do a good job? How fast is this algorithm? This type of questions are still open. What people have tried and got some success is that they proposed some variants of this, and then they got some success. But imagine like a paper with 70,000 citations is still open, like to be able to prove that there is you can consistently estimate, like you can consistently optimize this and things like that. What is there in the literature are kind of variants of that. So that is what something that we are like currently exploring, that is Adam RMS Prop. And I was also very surprised to explore that there is indeed a connection with what I know in time series to something like this. That so I will be very honest, I just knew the name Adam and RMS Prop. I never actually even bothered to look at it. But when I actually started working with this friend and collaborator, I think I got introduced to it, and then I realized, okay, maybe it still looks like time series, and then maybe we can do something here to understand how this progression works. So yeah, so that's pretty much where I would like to draw curtain today. I've like also tried to touch upon many different things. And if you have questions, I'm sorry to go overboard a little bit, but if you have questions now, you can ask me. I can go back to any slide you would want me to elaborate on.
Thank you very much. So this was indeed a really thought-provoking lecture. So we do have a couple of raised hands, and you may also type the questions in the chat, and we can take them up. So Akshay's unmuted.
Thank you, sir, for the informative lecture. I would like to ask a question on the portion where you were talking about spectral density. That is in the, especially in the graph about like where your example graph was on chicken prices and how and what kind of frequencies you can get, and in the but for what I have heard is like I have not yet encountered Fourier transform in my coursework, but Fourier transform is usually applicable to continuous functions, right? But this is a discrete data set. Then how can we apply it here?
Right, that's a good question. Like, so see, now if you like, I define the gamma h, right? I mean, I am saying that this is kind of an, like when I said it's Fourier transform, I did not say it's a Fourier transform of an entire function. But what I wanted to mean is that, see, gamma h can be defined as the covariance that you can have at lag h, right? So if I give you a set of gamma h, I can then define this function. I mean, this h is like sort of discretized from -infinity to infinity. So there is no one who can stop me from defining a function like this. And this can be defined over any omega whatsoever, like a continuous stretch of omega. Because this is like this omega, there is no restriction. Because remember, when we look at the period, we will do 1 over omega, and that will give us a sense of the period. And then we will discretize that period. Of course, we won't be able to, like, so say 1 over omega comes out at like 1.2 years. But 1.2 years could be meaningful in the sense it could be probably like 15 months or so, right? So 15 months is a meaningful periodic length. So, I mean, the problem of continuity really does not arise here, in the sense that when we talk about this period could actually be not integers as such. But then we look at models that are approximating that. In the sense, if the period comes out as 1.01 years, we will probably just say, okay, maybe it is meaningful to just introspect into like a 1 year period. So probably, yeah, it's not exactly what you do in like Fourier transform. But what I wanted to say was, like, when you take away Fourier transform of a function, you can retrieve it back. So we are doing something similar on this slide. Like from the gamma h space, like the autocovariance space, you can go to f of omega. And then the plot was about those f of omega. And then from the f of omega space, you can retrieve back the gamma h. That's what I wanted to say.
Thank you, sir. And maybe Hari, if you could.
Sir, I wanted to ask you whether these ideas can also be extended to panel datasets, or these are purely for time series.
It is indeed, like, I mean, it depends on like what you exactly mean by panel dataset. But indeed, it is like panel datasets when you have like observed multiple series over time. But I don't know exactly what you mean by panel data. But we do come across some of the datasets are termed as like panel datasets, where you look at each time point and then you look at the cross section. So whatever happens in that cross section is the contemporaneous correlation, like I was saying, like a spatial correlation, but that thing can also move. So I think a multivariate time series is what you can call like in panel, like call as panel data in some other applications. But yeah, it can be applied in panel data sets.
Thank you.
Thank you, Professor. So two other questions that we received were, I'll ask the first one. Intuitively, how exactly do the Fourier coefficients help in understanding the periodicity of the chicken price data set?
Right. So if you look at this, like you'd see that there is like a peak around like 0.2 here. So if you invert that, 1 over 0.2 gives me 5 years, right? So, and then you go back to the data, you see there is indeed like a period of 5 years, because after every 5 years, it has a tendency of going up. And then, so it goes up and then goes down, goes up and then goes down, goes up and then goes down. So wherever we see these peaks are important indicators of where we see these periods. And then of course, like it will start from like somewhere, and then you see here there is a peak, which is like the yearly period. So what happens is, like in time series data, of course, we always talk about very simplistic models, but in reality, there are many different driving factors. There could be like a seasonal period, there could be an yearly period. Here there is a 5-year period. So this sort of scenario, well, I mean, so if there's a mixture, it's very difficult to kind of segregate, like, and then factor out this sort of different periods to give us important insights. So spectral density helps us understanding these different peaks and the different possible periods that are there by going into the frequency domain.
Okay, sir. Thank you.
Okay.
Another question that we received was, you have spoken about periodicity in global temperatures. And the question we received was, what explains the period of temperatures every 60 to 70 years?
I'll be honest, I am not an expert in that, but that's a very good question. I probably should know when I'm talking about it, and I should be able to answer. I do not know exactly why this 60 to 70 years is there, but that's an interesting question. Maybe I should know better than this. But yeah, I do not know why, but there has been a trend of like 60 to 70 years where like this sort of periodicity, which is often like kind of shadowed by this increasing global temperature trend. People do not really see that, but when you actually like analyze it at a more minute level, then you can see this. But yeah, I apologize, I do not really know why there is, I mean, it also looked like pretty weird, like pretty surprising that there would be a period of 60 to 70, which I cannot really explain how. But maybe it has something to do with how, I don't know, how Earth orbits around sun and things like that. But yeah, I have no idea really, honestly. But it is like, of course, if that is the case, I mean, you also have to factor in the things like how industrialization has happened and like sped up in the last maybe 200 years, and like it's constantly growing, it's growing fast. So who knows that maybe in the next cycle of 60 to 70 years it will become shorter than that. It is possible. Like these external factors do play quite a bit of role. So yeah.
All right, sir. Thank you.
Thank you.
Anand, could you unmute and ask?
Oh yeah, hi Professor. Thank you so
Hi.
much. I really enjoyed the talk this time. So I have a question which is actually motivated by an example. Like I think someone was asking a little bit about having multiple variables, but like in particular, suppose let's say you have a disease like cancer and you wanted to, for a particular age, see its incidence over the years. Not incidence, the number of people of a certain age who have the disease. And you wanted to consider the family of these time series, let's say for each age, like maybe from 50 to 80, you had like around 31 times like series for people having cancer from the years, let's say 2000 to 2020. Right. So to predict in general, like anybody of a certain age X in this year T, right, having the number of people like in that year at that particular age having the disease, would it be better to actually look at these as a family of 31 different series and predict them, like apply those models? Or would it be better to take another time series, let's say the survival rates, right, for like people of a certain age, right, over the years? Because let's say people of age 50, if they survive, and the percentage of them surviving for 5 years is, let's say 40, right, versus people at 70 surviving for 5 years is like 25 or something like that. Using that to actually go between like these different time series, like in some sense, like
right. I think you can do both probably, but the survival rate looks more reasonable, but you'd have to take into account something that when you do some sort of transformation, then how the covariance is going to change, in the sense that whether the time series become more dependent on each other. Because I mean, you are looking at like survival rate up to age 40, so probably we're looking at data past 40. And I mean, when you actually have a data of like each year for each age, you have segregated data, but these data are correlated in some way. But when you are looking at survival data, you're probably aggregating the right tail and getting to a number. So you might want to be a little bit conscious about whether your data sets become more dependent because of that transformation. But yeah, so I won't be able to subjectively, I mean, I wouldn't be able to give an objective answer unless I can see an actual data and see how the numbers are behaving. But yeah, I would be a little conscious about if I am like doing like, so if you have x1, x2, xn, you can definitely always go and do the series x1, x1 plus x2, x1 plus x2 plus x3, and so on, right? If x1, x2, xn was dependent, so would be this transformation. But I would be careful, like, okay, if you are doing something like that, later transformation would become very, very correlated. So that might be like sort of destroying what we had initially about x1, x2, xn. But yeah, it depends on the data and the context. And I mean, without seeing it, it's very difficult to give an objective uniform answer to that.
And sorry, just related to this only, I wanted to know, like, if you increase the number of variables also, right, that you're looking at, does the same thing hold true, or is there like some other nice property about when there are a large
if you
number
increase the number of variables, what you can do is like you can do like a regression, in the sense you can have yi and this xi prime beta type of thing. You can regress out this yi on this sum of these interesting variables, and then you can look at the dependence on ei. So when we talk about models like this, let me go back. So when we talk about models like this, one of the reason we say this type of model yi equals xi prime beta plus ei is that to make ei as independent as possible, so that we can attribute all the relationships to this xi time series. So if you increase the number of variable, of course your variability, I mean, of course your reduction of variance would be significant, and then you can proceed accordingly. But yeah, I mean, increasing variables could help you. But again, it depends on the context. Like if you throw in some of the variables that are not really related, that it could be a little bit misleading. So you always have to test whether those variables are at all significant or not. So I mean, if they are indeed significant, then maybe it would solve your problem. Yeah.
Okay, thank you, Professor.
Thank you.
Pankaj, could you?
Sir, could you again please explain what autocorrelation and ACF plots are exactly telling us? What exactly are they telling us?
Yes. So where were we here? So the ACF is autocorrelation function. So this gamma h is correlation between xt and xt plus h, covariance between xt and xt plus h. So if you know covariance is a measure of association, in the sense, if you see a positive autocorrelation, say this number is 0.3. So if you give me yi, I know yi plus 1 is going to be 0.3 times yi. It's going to decay in this fashion, plus some small perturbation ei. So once we look at this ACF plot, once we know this number rho 1 is how yi is related to yi minus 1. So if I do a plot like that, and if I see rho 1 is coming out to be 0.3 from this type of thing, of course we have to do like statistical tests, but that will give us an idea that if I know my yi minus 1, my best guess for yi would be 0.3 times yi minus 1. That is exactly what an autocorrelation plot is giving me. In this context of time series, it also, like looking at all these autocorrelations together, also helps us decide what would be an appropriate model. Should we do it via autoregressive model? Should we do it via MA model? Should we do it via like an autoregressive MA model, arch-garch, etc., etc.? But the number 0.3, probably what you are trying to ask is, if you see the number 0.3, what it means is, if I see my yi minus 1, I would expect my yi to be 0.3 yi minus 1 plus ei. So that can give me a best case for what the future is going to be. So from a forecasting perspective,
the blue line is helping in finding the estimate.
No, the blue line is not. These are the estimates. The blue line is trying to tell you whether these estimates are significant or not. If it is above the blue line, that means it is significant, in the sense this 0.3 is not just by due to some random fluke or chance, or like just because of this data set itself. If you just like just because of the numbers that you are observing. So sometimes you see, like when you collect the data, you collect certain amount, like certain like you have a certain data set. I collect a data, I will have a different data set, right? But we are collecting data on the same variable. You have one coefficient, I have another coefficient. Now, will we start fighting like, okay, whose coefficient is right or not? I mean, you are getting a coefficient like say 0.7, I am getting a coefficient of 0.5, but we want to know whether this 0.7 and 0.5, this difference makes any sense or not. So similarly, if we see an estimate, say 0.1, of course, we would be, I mean, we are seeing a non-zero number, but how do I know that this number is a significant number, in the sense this number was not just due to random fluctuation or like random fluke or random chance? So that is what this blue line is doing. The blue line is saying if it is above the blue line, that means it is indeed significant, and you should not rule out that the autocorrelation at lag 1 was just 0. If it was below the blue line, then it would mean that it is probably, I mean, just this is probably a property of just the data set, that autocorrelation at lag 1 is coming below this blue line. It is like, I think your question is probably not tied with this time series or autocorrelation part. It is just a simple linear regression question. If you look at yi equals xi prime beta plus ei, if you estimate one coefficient, then what exactly, how would you understand whether this coefficient is significant or not? So that is what we are trying to do here. The blue line is just that line of significance for these estimated coefficients.
Thanks very much for the lecture. So I'm sure there will be many others who have many other questions. So right. If you do happen to be one of them, do write to us on our official email ID, and we can get them answered by Professor Sayar.
Right. So I think I'll just answer this one last question. How are you determining the blue line? The blue line is typically around 1.96. That's the normal threshold cutoff. So that's how we determine this blue line. So blue line, of course, for different problems, different blue lines are used, like different regression problems, different blue lines are used. I am not determining it. It's kind of like a theory that there is that like this blue line above this, there is significant, otherwise it's not.
Thank you, sir. So now we can come to a formal close of the session. So do join me in thanking Professor Sayar for this wonderful lecture, giving us an insight into your own research and some very practical applications of this seemingly weird concept called time series, like its applications in agriculture, stock markets, medicine, meteorology, and everywhere. So this was really a wonderfully delivered lecture. So we meet again tomorrow at 7:30 p.m. IST, where Professor Ryan O'Donnell from the Carnegie Mellon University will be talking about quantum computing. So he has promised us to show some magic tricks and what quantum computers do that classical computers cannot. So let's see you again tomorrow, and have a very happy and safe Diwali. So thank you very much again, Sayar.
Okay. Thank you so much. Thank you. Thank you. Thank you. It was a pleasure. Thank you for attending. Thank you for spending your time.
Thank you. Have a good day. Bye.
Yeah, you all have happy Diwali as well. Yeah.
Thank you. Thanks.
Thank you for organizing. Thank you.